I chose the problem of modeling the molecular orbitals of pi electrons in conjugated systems using the Huckel molecular orbital method. We want to model conjugated molecules, that is, those with systems of connected p orbitals with delocalized pi electrons. A few examples are benzene, an allyl radical, and cinnamaldehyde. As you can see, each of these molecules exhibits resonance in a sharing of pi electrons. In the early 1930s, Huckel formulated a model that reproduced, theoretically, many of the observed properties of unsaturated molecules, including the uniform carbon-to-carbon bond length of benzene, the high energy barrier to internal rotation about double bonds, and the unusual chemical stability of benzene, which does not react like a normal alkene because it is resonance stabilized. The basic idea is to treat only the pi electrons explicitly. Clearly, ignoring the sigma electrons is an approximation, but hey, it works. We think of the pi electrons moving in a potential field due to the nuclei and a sigma core, which we assume to be frozen as the pi electrons move about. We also assume that the pi electrons are independent of each other. So, let's look at the simple case of an allyl radical, C3H5. It's a planar molecule with 3 unsaturated carbon centers. You might be familiar with the Lewis structure. We can see that it is in resonance. To model the system, we ignore the orbitals involved in sigma bonding and just look at the orbitals in the pi system, namely the 3 pz atomic orbitals. Our basis functions are chi1, chi2, and chi3, which are the wave functions that represent a single p orbital. The wave functions for the 2 pz orbital is represented by this equation. Each carbon atom is uniquely identified by a subscript, which will be important in setting up the Huckel determinant. We perform a linear variation calculation using this basis set. This will lead to a 3×3 determinant whose roots will be the molecular orbital energies that can be used to obtain the molecular orbital coefficients. So, this is the determinantal equation. I will go into further detail about the two integrals at the bottom. When I equals j, then this is the Coulomb integral, and h equals alpha. When I does not equal j, then this is the resonance integral. H equals beta when I and j are neighbors, and h equals 0 when they are not neighbors. As you can see, carbon 1 is adjacent to carbon 2, and carbon 2 is adjacent to carbon 3, but carbon 1 is not neighbors with carbon 3. Therefore, H12 equals H23 equals beta, and H13 equals 0. S is the overlap integral. If I equals j, then s equals 1, and if I does not equal j, then s equals 0. These are approximations, but the qualitative solution still holds. Now our determinantal equation simplifies. We divide everything by beta and say that x equals alpha minus energy over beta. This leads to a simple Huckel molecular orbital determinantal equation. The 1's represent bonds, and the 0's represent a lack of bonds. The determinant is always symmetric for reflection through the diagonal of x's. Solving for the roots produces values of 0, root 2, and negative root 2 for x. We find that the corresponding energies are alpha plus root 2 beta, alpha and alpha minus root 2 beta. So, the system has split into 3 molecular orbital energy levels. The next task is to find the coefficients that describes the relative contribution of each pi orbital. Therefore, we solve the equations for each value of x. Herein lies the power of the Huckel method. Through simple assumptions, we are able to tell the relative energies of the molecular orbitals and the corresponding signs and magnitudes of the atomic orbitals. Using Mathematica, we can make lovely plots of the molecular orbitals. The lowest energy molecular orbital, phi1, which is bonding in the C1, C2, and C2, C3 region, because all the pi orbitals are in phase. We can see that the electron density on C2 is greater, which agrees with intuition. The second lowest energy molecular orbital, phi2, is non-bonding. The high energy molecular orbital, phi3, is everywhere antibonding because none of the orbitals are in phase. Now we can move on to modeling benzene. Let's number the carbon atoms 1 through 6. The same principles apply. We find the Huckel determinant and solve for the roots, which equal -2, -1, -1, 1, 1, and 2. Immediately, we can see that we have 2 degenerate energy levels, that is, they are at the same energy. First, we will plot the lowest energy level corresponding to x equals -2. We can see the qualitative nature of the solution with all the pi orbitals in phase to produce bonding between each of the carbon atoms. The figure on the right represents surfaces of equal probability density. The figure on the left represents a slice of the previous plot along the y equals 0 plane. These curves are level sets of equal probability density. Now we take the level sets and set x equal to 11/2, which is where one of the carbon atoms is located in my model. The graph shows the probability densities plotted as a function of z. Because this is not normalized, we cannot conclude quantitatively what the highest probability density for the system is, but we can see that there is a maximum probability of finding the electron located around z equals 2 and z equals -2. There is 0 probability of finding the electron at the nodal plane. In Mathematica, we can also find the solutions for all the molecular orbitals corresponding to the energy levels found using the Huckel method. This is the plot of the highest molecular orbital, and the bottom two plots correspond to the degenerate molecular orbitals with the second highest energy. We can see the qualitative nature of antibonding solutions. The top figures are the degenerate molecular orbitals with the second lowest energy, and the bottom figure corresponds to the lowest energy molecular orbital that we solved for before. These are the bonding solutions of benzene. Finally, we can put all these figures together to generate the molecular orbital diagram of benzene. Using Mathematica and just a few simple assumptions of the Huckel method, we were able to model the molecular orbitals of pi electrons. This is a very powerful tool that can be used to model more complex conjugated systems. Thank you very much for listening to my presentation.